Really sorry for being late today. So good morning. This is RFIC, and today we'll start our unit 2, second unit. So in unit 1, mainly we discussed about two major issues in RFIC, and we stated it as one is non-linearity and another one is noise. So am I audible?
Yes, sir.
Okay. So we discussed about two things. So and we in unit 1 we discussed about non-linearity in very detail, various performance parameters, and we have looked at the evaluation arriving at 1 dB compression point, harmonic distortion, then IM3, AIP3 values, and the cascaded structure of AIP3, all those things. Now in this unit, in unit 2, we will continue uh, the discussion of we'll continue the discussion of the other major issue in RFIC, which is noise. So before we start noise, we have to look at two more additional things. So let us finish that and then we'll directly start with noise. So this is your unit 2 RFIC, and noise in RF circuits. So in the introduction class, when we compared between analog design engineers and RF engineers, we stated that uh, in analog design or in analog and mixing IC design, we discussed about noise in a circuit, and we expressed that in terms of nanovolt per root hertz, either in terms of RMS value or in terms of mean square value, right? So root mean square or mean square value, and we also expressed in terms of power spectral density, PSD. Right now, in here in RF or RF designers generally use the concept of noise figure. So it is a measure expressed again in decibel. So RF designers use the concept of noise figure. So before we start anything in detail about noise figure, I have to look at two more things. Uh, Noise figure. Okay. So I hope you would have heard about noise figure even in your communication system courses. Can I get some response in chat box? Are you aware about noise figure? Have you heard about this performance metric? Can I get some response? Output noise by input noise, maybe. Okay. Any more response? Degradation on SNR. Okay, very good. All right. Yeah. So this noise figure is in fact this degradation of SNR itself. So noise figure can be defined as the degradation of SNR of signal to noise ratio as a signal travels through a circuit or through a system. So as a signal travels through a system, definitely, if in a practical system, the system itself will add some noise that will make the signal to noise ratio to degrade when it travels from input to output. Say, for example, you have a system and this is input and this is output port. Now, at input, you are receiving a signal. Say you are receiving a signal SI with a particular signal to noise ratio. So now, as this signal travels through the system also will add some noise. And at the output, if you measure the, say this is signal to noise ratio at the input, and this is signal to noise ratio at the output. So the system is adding noise, then there are chances that the entire signal to noise ratio can drop. So now that depending on the strength of the signal at the output, the amount of noise which is added by the system. So in order to measure this, we have this performance parameter. We call this as noise figure. And to evaluate noise figure, we write noise figure is actually equal to SNR in by SNR out. Sometimes the inverse of this, which is SNR out by SNR in, yes, Rakshak, noise figure should be less. Yes, the amount of noise added to a system should be less, or as a signal travels through a particular system, uh, its SNR should not degrade so much, right? Yeah, in that way, noise figure. Yeah, we will come to that. Yes, so noise figure is basically we express it as SNR in by SNR out. Now, for everything to start, whenever we discuss about something, we always discuss with an ideal system. So, in this case, I would say an ideal system is a noiseless system. Say, for example, for a noiseless system, so for a noiseless system, what will be noise figure? If the system is not adding noise to the system, we can, yes, noise figure can be considered as 1. Right, system is not adding noise. So whatever is coming in, the same signal I am getting at the output, though there is no addition of noise from the system, right? So in that case, the input SNR and output SNR will be almost same. Again, we used to express this noise figure in decibels. So noise figure is denoted as NF. We express that in dB. So if it is in dB, we will write this as 10 log of SNR in by SNR out. This is noise figure in dB. And this is, in some literature, they call this as noise factor. When we express that in decibels, we call that as a noise, we call that as noise factor, right? So we will discuss about noise figure. We will arrive at an equation through by considering a system. Again, we will also consider cascaded systems and see how noise figure um, degrades, or what is the noise figure of a cascaded system. We look at all those things. Before that, we will just see another two things. One is called as sensitivity of an RF system. Sensitivity, and another thing is dynamic range. Sensitivity and dynamic range, right? So these are other two performance metric, or other two definitions we should understand in order to design any RF system. So let us start with sensitivity. So what is sensitivity? What do you understand when you hear sensitivity? Any idea? Can I get few response in chat box? Minimum signal the system can detect. Very good. Can I have Ashwin here? Ashwin Harish. Whether Ashwin Harish is there? Ashwin? All right, okay. Yes, the minimum signal the system can detect. Inverse of quality factor. Actually, I didn't get that. Response to small changes. Okay. How is the SNR defined at the output? Because we have other components than the signal. Oh, you're asking a question, Saurabh? SNR is defined at the output as the output signal component to the output noise component. Oh, you mean to ask? Yeah, we are basically looking. So whenever we generally say SNR, we are referring to the fundamental component. We are referring to the fundamental component. Probably I can answer that, Saurabh. Just wait for a while. How much a particular circuit characteristic changes? Okay, 1 by q bandwidth. Rakshak, I think you are referring to selectivity. Are
Oh
you?
yeah, selective.
Yes,
Yes, sir.
yes, yeah, yes, yes. Yeah, Saurabh, so your question is good actually. So we will see that whenever we define sensitivity, or basically when we define dynamic range, we will also state that dynamic range is in fact in RFIC design, we define it in a little elaborate way. We call it as spurious free dynamic range, or SFDR, where we will not consider, or we are looking for a range where you will not have any other unwanted frequency components. Now, if Saurabh, if your question is whether the output intermodulation components or any other components which if you're referring to that, yes, we will define that in dynamic range. Yeah. So, Saurabh, if you want, you can unmute and just give a clarity on that.
Yes, sir. That was my question.
Yeah. So basically, we define signal to noise ratio by considering the fundamental component. But even the other components, we will bring that also into picture. So we will see that very shortly. In dynamic range, we will define that. Right. Okay. So sensitivity, as many suggested, it is the minimum signal level that a receiver can detect with acceptable quality by satisfying minimum signal to noise ratio conditions. So I'll define it as it is the minimum signal level that a receiver can detect with acceptable quality that is by satisfying minimum SNR requirements. So for any system to detect a signal, so we know that when in a receiver, it is not that a single block or a single circuit. We'll have a chain of blocks, or chain of circuit blocks will be there. So we decide sensitivity basically by looking at the minimum signal to noise ratio requirements for the entire system. Right. So let me start. So what we are going to do now is to arrive at an expression for sensitivity, so that we can use that to detect the sensitivity of any system. Right. So to start with, I'll just write what is noise figure. So noise figure is something what we have just discussed. It is SNR in by SNR out. Right. Now, in this, if I am defining what is this SNR in, so SNR in can be defined as the signal power which is available at the input to the noise power which is available at the input. So I am referring to something like this. An antenna is there, and you have, this is a receiver, and this is the first block. Probably you can consider this as an LNA, or there is a filter before LNA. So this is the receiver block. Now, if I look at the signal to noise ratio at the input, I can write SNR in as the signal power available. So I'll write it as P signal divided by the noise power. So that noise we define with respect to the antenna resistance. So if you remember, we know that resistance will have its own noise. So in this case, if you define signal to noise ratio at the input of an LNA, we generally define that SNR by considering the signal power and the noise power, and the noise power is actually given by the antenna resistance. So we write it as P. The resistance of the antenna, we call it as RS, the source resistance. So this is how we define signal to noise ratio at the input. P signal to P noise. Noise is from the R, the source resistance. So, or this antenna can be, we can model this antenna as a signal source with some resistance RS. This is actually the input. Right. Now, from this, if I write what is the signal power, I can write the signal power as SNR in, the input signal to noise ratio, multiplied by the power of the noise power, right? That is also straightforward. Now, what I'm doing here is, so I am looking for the minimum signal level. So I define sensitivity as a minimum signal level. So that is why I'm taking the P signal as the left hand side expression. I'm trying to get an expression for that. Now, when I consider minimum signal level, that should be with acceptable quality, and that also should satisfy the minimum SNR requirements, right? So I am bringing in all those things together here. So SNR in. So if I write SNR in from here, so from this equation, the input noise signal to noise ratio can be written as noise figure into SNR out, right? So I am substituting that over here. For SNR in, I will write it as noise figure into SNR out into the noise power from the antenna resistance, right? So this is the signal power. Now, now this the input signal power depends on the bandwidth also, right? So say if the system, if you are receiving signal power for such and such so and so bandwidth, then we can write the total signal power for the entire bandwidth. Total signal power can be written as, say, P signal total, that can be written as noise figure into SNR out into PRS into B. B refers to the bandwidth of the system, right? Now, this is the total signal power. Now, if I define this as sensitivity by writing this as P signal minimum, then I will modify this as noise figure into this SNR out is actually the minimum SNR, and this is PRS, and this is B. So this is often or this is the expression we generally use in an RF system to define sensitivity. So sensitivity is the minimum signal level that a receiver can detect with acceptable quality by satisfying a minimum SNR requirement. So you can see the SNR minimum has brought in here by bringing in all the other expressions into this, right? So this is sensitivity. But again, since this is expressed in power, we will write all these things in terms of dBm or dB. So this sensitivity will be written as P signal total, which is in dBm, power level, equal to noise figure in dB plus SNR minimum in dB plus the noise power in dBm plus bandwidth 10 log of B. Right. Now, let us define what is this PRS also. So the receiver noise power, sorry, the antenna noise resistance or the noise power at the input is calculated as this value is equal to, this power is equal to KT, and in dBm the value is minus 174 dBm. Standard value what we use, it is minus 174 dBm. Now, putting this into the above equation, I can write this P signal in dBm as minus 174 dBm, which is actually the noise power, plus the noise figure in dB, plus 10 log of bandwidth. I'm just rearranging the terms, plus SNR minimum of the system in dB. So why I have rearranged this term is, if you look at the first three terms, one is the noise power, other one is a noise figure, and the other shows the entire bandwidth. So across the bandwidth, you can see that minus 174 dBm plus NF dB plus 10 log bandwidth is actually showing contribution of the total noise, or this is often defined as total integrated noise of the system, or this is also defined as noise floor level, NFL, right? So with that, if I redefine P signal, the sensitivity or the minimum detectable signal power is equal to the noise floor level of the system plus SNR minimum. So this is the expression for sensitivity. So where did I start? I started by defining sensitivity as a minimum signal level that a receiver can detect with acceptable quality by satisfying minimum SNR requirements. Then I defined noise figure. From that I wrote what is SNR in. Then I defined signal power from the same expression, and then express the total signal power by multiplying with bandwidth. Then I introduced the receiver noise with the constant kT as minus 174 dBm, and then included in that and defined what is the noise floor level. So you can see that in any system, there is some acceptable range of noise. That is what is defined as noise floor level, because we are not looking for a noiseless system, or if we cannot expect a noiseless system. System will be noisy. So we are including even that. Now your minimum detectable signal level should be actually more than that level. So if it is buried inside this noise floor level, it cannot be detected, right? So the signal level should be more than the noise floor level with the minimum SNR requirement. That is what you can see from the definition of the sensitivity. Now continuing with this, if you have doubts, you can just put in chat box. We'll have discussion at the end. Let me just finish this dynamic range also. So we define sensitivity here as the minimum signal level with minimum SNR requirements. Now let us look at what is this dynamic range. So any idea what is dynamic range, or have you heard about this dynamic range before? Any response in chat box? Maximum possible output of the system. What is the second one? Range of? I didn't get that, Rakshak. Range of Vmax minus V minimum in ADC DAC. Yes, you would have heard about dynamic range in ADC, right? Range of Vmax and V minimum. Okay. Range of Vmax and all right. Maximum to minimum values that the input takes to give a suitable output. Very good. Oh, Ashwin, you are there. Range of operation. Okay.
Yeah, sorry, sir.
Yeah. All right. No problem. Okay. Yeah. So dynamic range is, yes, whatever you have stated there in the chat box is almost similar. So dynamic range is generally defined as maximum. So we define that in terms of input. Even we will refer the same thing at output as well. So maximum input signal that a circuit can tolerate. maximum input signal that a circuit can tolerate to the minimum input signal level with minimum SNR requirements. Right. So dynamic range is the maximum input signal that a circuit can tolerate to the minimum input signal level with minimum SNR requirement. So probably you'll identify that as the sensitivity of the receiver, right? So yeah, so as I mentioned before, probably I can just show how to uh, define dynamic range in general. So if I am looking for a, so I'm looking at the spectrum, output spectrum. So probably you can assume that this is log scale. So so dynamic range is actually the difference between or the ratio of minimum maximum input signal and the minimum input signal, right? So let me start defining the minimum input signal level. So say this is my minimum input signal level. This is my minimum input signal level. So this is nothing but my sensitivity. Right, this is the sensitivity. Now when I define sensitivity, I'm sure that there is something called as noise floor level or the total integrated noise of the receiver. So this is noise floor level, and the signal level should be more than noise floor level by SNR minimum. So I hope this is clear. I define sensitivity. So this is my minimum detectable signal, which is higher than noise floor level by some suitable value, and that is the minimum that deals with the minimum SNR requirements. Now, this is a minimum sensitivity. Now, maximum is a circuit can tolerate. So, how much ever I can give to the system, how much the circuit can tolerate. So, how can I identify that? So, the circuit can tolerate an input system until it is either limited by the power supply, or even before we have seen that definitely for this is if the system is non-linear, the system will eventually compress. Almost all systems have compressive behavior. So basically it is gain compression, right? Or gain compression, or it can be the supply limit compression as well. So let me define that somewhere here. So you will actually get, this is your maximum level, but if you move above this, or this level is defined as above this, if you go, it will be compressed. So this is the compression limit. You can write this as compression limit. And dynamic range can be defined as the range between these two. So this can be defined as dynamic range, right? So the minimum input signal that a circuit can tolerate to the minimum input signal level with minimum SNR requirements, right? Now, so this is actually, even though we define in terms of input signal level, whatever I'm showing it is actually at the output side, or you can, so this whatever I have drawn here is actually with respect to the compression level. So it is in fact I'm defining at the, or what I'm marking is actually the output signal levels, right? Okay, so let me move further. So let me define what is important in an RF system. So in RF systems, we have a slightly instead of dynamic compression, we define something called as uh, SFDR. In RF systems, we are looking for SFDR, where SFDR means spurious free dynamic range. Or the spurious, or this has come from this word spur, and in RF or generally in communication, spur is any unwanted frequency component. And in our case, we are definitely referring this to the unwanted components appearing at the output apart from the fundamental components, right? So fundamentally is what we really want, but other than fundamental, we know that we'll get a lot of other frequency components because of non-linearity. So in a non-linear system, or typically in an RF system, considering it as non-linear, we define SFDR. So how to define this SFDR is, so SFDR can be defined as maximum input power for which, so if I look at the other components which affects the output fundamental, the prominent one among that is IM3 components, right? Because those are the components which are coming very close to the uh, output fundamental. So we are defining this SFDR with respect to those IM3 components. So SFDR is defined as the maximum input power for which IM3 products lie below the noise floor level. So we defined a noise floor level, which is so that is actually comprising of the entire noise of the system. Now you can think about a maximum input power. So as you increase the input signal power, your output signal power also will increase. Along with that, see, we have seen that the IM3 products are also proportional to the amplitude, right? Amplitude of the input signal. So as you increase the input signal power, IM3 products also will rise. Now, what is considered as a maximum input power in this case, such that your IM3 products are not peaking above the noise floor level? Let us define that more precisely. So, to the minimum input power with minimum SNR requirements. Right. That is again referring back to the sensitivity. So let us try to get an expression for this. For that, I'll take the previous expressions what we have derived in our first unit. So one is we defined IIP3, the power level, as the input power level plus delta P by 2. And if you remember, this delta P is was defined as this one. So this is a fundamental component and this is IM3, and delta P was actually defined as this difference, right? So I am just taking that equation. Why I'm taking that equation is, let this be equation number 1. Now I can define this delta P. What is this delta P? Delta P is actually the output signal power and the difference between the output signal power and the output IM3 products power. So delta P can be defined as P out minus P IM3 at the output, right? Now okay, so now in order to get an expression, let me define few more things here. So P out, the output signal power, if it is in dBm, I can write it as input signal power in dBm plus gain of the system in dB. So input signal power and output signal power are related by gain, or the difference is gain itself. So similarly, even if it is not completely true, I can definitely write that this PIM3 out. So if I am referring to the IM3 components at the output, that also will be related roughly with PM3 in with G, even though we have some other terms, not the exact gain, but we can roughly state that the output signal power and the input signal power are related by gain. So since the system is providing a gain of G, even the IM3 products will also have a similar behavior. If that is the case, if I write this P out minus PIM3 out, that can be written as, or that can be equated to P in minus PIM3 in. So let me just number these equations, because I'm trying to define SFDR by including IM3 products, but I have to refer back that to the input. That is why I'm just getting these equations. I hope you understood. This is the same equation what we have taken from unit 1, and then I defined what is delta P. Delta P is this difference. Now the fundamental component at the output and input are related by gain. The similar expression is similar relation is taken for IM3 products as well, and define the difference between the output and output IM3 as same as the input signal power and the input IM3. In fact, there is nothing at input as IM3, but we are referring back to the input by relating that to the gain expression. Now if I am yeah, so now what I'll do is I write IIP3 as, so IIP3 can be now written as P in plus delta P is in fact P out minus P IM3 out, but that is equal to P in minus P IM3 in. So I'll write here it as P in minus P IM3 in. This is delta P by 2, and this is your equation number 4. Now if I just rearrange this equation, because I am looking for the input signal power, right? Because to define dynamic range, I should know what is yes, Rakshak, your question is how can there be IM3 products in the input unless in the second stage of the cascade? Yes, so that is what I was telling. IM3 products will not be at the input of if you define a system, a single block, IM3 products will not be there at input. So in order to get the expression for spurious free dynamic range, and to state that the maximum input power should be such that your IM3 products lie below NFL, I am referring the IM3 products back to the input. So IM3 products are available at the output. So if I consider the system is providing a gain of G, the IM3 products can be refer back to input by just subtracting with gain. That is what I have done. In reality, there is no IM3 products at the input. That is true. Yes. So if I rearrange this term, P in can be written as 2 IIP3 plus IM3 products at the input divided by 3. By rearranging, you will get this. So this is the input signal power, right? Now, so in this input signal power, even I have brought in IIP3 also. So this is giving you a hint that I am referring this to the maximum input signal power, right? Now, by the definition of SFDR, what I stated is maximum input power for which IM3 products lie below NFL, right? So now you can see that there is a component here as IM3 in, the IM3 product, and I know that that should lie below the minimum noise floor level. So that means I will redefine this as P in maximum. So this can be P in maximum when this PIM3 in should be less than NFL, or maximum it can be till noise floor level divided by 3. So I substituted the IM3 in, or the IM3 products equal to the noise floor level. IM3 products should not peak out of this noise floor level. That is idea there. So this is P in max. Now if I write what is P in minimum, that is same as sensitivity we defined before in terms of noise floor level and SNR minimum. So that now both are in terms of noise floor level, SNR minimum, and IAP3 of the system. So now to define SFDR, or spurious free dynamic range, it is just the ratio of these two. So P in max minus P in minimum, assuming that all are in decibels, dB. So it can be written as 2 by 3 IIP3, sorry, no. Yeah. So it will be 2 IIP3 plus noise floor level by 3 minus NFL minus SNR minimum, or this can be further rearranged to get this expression as 2 by 3 IIP3 minus NFL minus SNR minimum, right? Now to look at this dynamic range, so even though we defined at the input side, similar to this how we define this dynamic range here, we will also define spurious free dynamic range by drawing the spectrum at the output as before. Probably you can mark this as the noise floor level, and this has the sensitivity. This has sensitivity and this has noise floor level. And now probably I'll draw components like this. So these are the fundamental components, and there will be IM3 products. So IM3 products I am marking like this, such that IM3 products are within the noise floor level, not more than that, right? In that case, I can define sensitivity as, so this is maximum, such that, so see how are we drawing this? We are looking at the output of the system by varying or changing the input signal power. So we are keep on increasing the input signal power and making sure that your IM3 products are just equal to the NFL, or it can be lesser than that. So till then we are increasing the input signal power and looking at the output output component such that your IM3 products are falling below the NFL. So this range is defined as spuriously dynamic range. So even though we define with respect to input, we can really look at the system, but so we can look at the output and see or say, in dynamic range we told the maximum the tolerance level, so that can be understood by only looking at the output, not just by looking at input. So this dynamic range or spurious free dynamic range can be well understood by looking at the output with respect to input. That is why I have just marked in this form. All right, so these are two very important things we should understand for a system. One is sensitivity and another one is dynamic range. All right, Sarvesh. In the SFDR expression, shouldn't the 2 should only be multiplied to IIP3? Oh, did I made a mistake? Are you referring to this 2 here?
No, sir. The after the rearrangement,
Oh, this one.
that expression, sir.
All right.
Yes, sir.
What I have done is I have just rearranged this. So will I not get that?
So 2 by 3 NFL minus NFL should be only minus NFL by 3, sir.
All right. Okay.
So the 2 should not be multiplied.
Can you just try, because when I have written like this, others can also try and let me know. I'll also check. Okay.
I'm
Sir, it
sorry,
should
sir.
be NFL by
That you
2.
found it this way.
It's right, sir.
Okay. Okay.
It's right, sir. Sorry.
All right. No issues. Okay. So now if you have questions, you can ask now. Let me